Cambridge English for Engineering by Mark Ibbotson, published by Cambridge University Press. This recording is copyright.
CD2.
6.1.
So with regard to the capacity, in terms of the number of people it actually needs to carry, what sort of figure are you looking at?
36 is what we're aiming for.
If you think we can add a few seats without making compromises, then by all means, let's look at it.
I think 36 is going to be at the top end as far as size is concerned.
And as regards the graphics, is the video sequence finalized? Will it be exactly as it is on this DVD?
Unless you have any problems generating the physical effects that go with it, then yeah. As far as we're concerned, that's it.
Right, excellent. We can start looking at that straight away then, and get things moving. So regarding the schedules, and what sort of timescale do you have in mind for the whole project?
6.2.
In terms of the physical effects, to what extent do you want the experience to be physical? The degree to which it moves can be varied quite considerably.
Well, I mean, we want it to be physical. That's why we're having a dynamic simulator. But we obviously don't want it to be so extreme that people are closing their eyes and not watching the amazing graphics we've got.
Sure. I mean, it's obviously difficult to quantify something like this in theory, sitting in a meeting room. The only way to determine what's right is to actually sit in a simulator and experience it yourself in practice.
Of course.
So what I'd suggest is, after the meeting, we can strap you in to one of our machines and you can assess the possibilities.
Sounds interesting.
6.3.
It obviously has to be lifted with a crane.
Yes, but do the slings necessarily have to pass under the base? Why not come up with a way of hooking onto the side of the statue?
How?
Well, couldn't we drill into it, horizontally, and insert bars into the holes? Then hook onto the bars.
People would see the holes afterwards, though.
We could fill all the holes, couldn't we? Surely they could use some sort of filler that's the same colour as the stone.
They'd never hide the holes completely, though. It would still leave marks, wouldn't it? I don't think that would be acceptable.
Or, alternatively, we could make sure the holes were out of sight. What about drilling into the top, vertically? If the holes were right on the top, they'd be less visible. Then the bars could be set in, with lifting eyes on the end.
The trouble is, if the bars were set in with resin, they'd never come out. They'd have to be cut off, wouldn't they? And this mammoth's lying down, so the top will probably be seen, to an extent.
True.
To be honest, I don't think we can envisage drilling into it. I suppose another option would be to use some sort of grab on the end of the crane jib. You know, like the ones they use for offloading lorries. So the statue would be held by friction. But I can't imagine there being anything capable of lifting 36 tons, especially not something that wide.
No. Have you spoken to the masons about this?
Not yet, no.
Why don't we ask them?
6.4.
So, all the steel beams shown on this drawing are going to be fixed to the walls, bolted through the concrete.
Right.
So, to bolt through, obviously, we need holes in the walls. We can core drill them with a diamond drill, which would obviously be done after the walls have been cast. We drill them ourselves as part of our contract package. Alternatively, the holes can be preformed by putting plastic tubes into the concrete when they cast the walls, in which case the contractor responsible for the concrete structure would do the job.
Okay.
Now, the problem is these bolts won't have much play.
How do you mean?
Well, they've got to fit quite tightly in the holes, so they won't be able to move much. There won't be much space around them to adjust their position.
I see.
So that means the holes have got to be positioned very precisely. If they're slightly out of position on the wall, they won't match up with the holes that have been pre-drilled through the steel beams at our factory.
Sure.
That's the main technical issue in terms of deciding how we form these holes. Obviously, the technical side's not the only consideration. There's also the question of timescales, given that there are a lot of these holes to do, and obviously the question of cost as well.
6.5.
In terms of cost, preforming is obviously a lot cheaper because all you need are plastic tubes, which are cheap to buy and quick to put in. If we do it that way, it'll be dead easy and it'll cost peanuts. Whereas core drilling will be slow, it'll be quite a painstaking job. But
core drilling's more accurate, clearly.
A lot more accurate. I mean, sometimes you can get away with preforming. If you need to get within 20 mil, then it's perfectly feasible. 10 mil it's achievable, but it's stretching it. Anything less than 10 mil, and there's no way you can do it.
And what sort of tolerance are you looking for?
About 10 mil.
So it's borderline then?
It's a tall order. The safe bet would be going for core drilling.
The problem is going to be the schedule, though.
Exactly. I mean, to diamond drill the number of holes we're talking about will take,
It'll take forever and a day, won't it? Whereas if they're preformed, they'd be ready as soon as the walls are cast.
But if half of them are in the wrong place, it'll cost an arm and a leg to put them right. Because if they're wrong, it's not just a question of drilling new ones in the right place. If they're slightly out of position, they have to be filled in first with cement, to avoid having two holes overlapping. So putting them right is easier said than done.
Sure. So, as I see it, the key issue here, in terms of feasibility, is the tolerance. If the holes can be bigger, and there's more play for the bolts, we won't have this problem.
6.6.
So, to be clear about how far we can go with this redesign, we're not aiming to reinvent the wheel in terms of the main components and how they fit together. The reasons for that are, firstly, from a hardware point of view, the existing design has proved to be effective, and secondly, we don't have the resources at this point in time to make fundamental changes to the production process.
So the overall internal layout needs to remain the same?
Yes. We're looking for an evolution rather than designing the whole thing from the ground up. Presumably there is room for improvement?
Well, this model has been revamped once before, of course, but no doubt we can refine it a bit more.
However, given that software redesign isn't an assembly issue and has been the Achilles heel of the existing model, it would make sense to rethink that whole system.
So, for software, back to the drawing board then.
Well, whatever we do, we need to make a quantum leap. Whether that means designing the system from scratch, I don't know. We need to make the whole thing much simpler to use.
7.1. A.
Next week they're due to start maintenance work on the grain silos in Zone 4. We need to make sure that everyone's aware that all those silos are classed as confined spaces. In other words, no one should go inside them without first doing an air test. And we need to keep a check on dust levels as well.
We've got a CO2 detector here, haven't we? B.
If you walk past that machine while it's running and you're trying to talk to someone, you have to shout to be heard. And as a rule of thumb, that means it should be an ear protection area.
Yeah, but the regs differentiate between brief exposure, when you're walking past something, and continuous exposure, don't they? C. So, is it harmful if it splashes on your skin?
According to the notice, it's an irritant and it's toxic.
But it's not corrosive.
Not as far as I'm aware.
So you don't need gloves and eye protection and masks and all the rest of it? If you get any on your skin, you just wash it off.
I'm not sure about that.
D.
We need to inquire whether or not this maintenance involves welding. There are forklift trucks going through that area carrying flammable liquids. If there are going to be any naked flames or sparks, we'll need to put a proper procedure in place.
Right, I'll get in touch with their people then. 7.2.
So in terms of access, theoretically, there's a risk of someone falling as they climb up a silo or down into one. But there's always an external staircase with a guardrail leading to the top, and there are permanent ladders with protective hoops around them, fixed to the insides, leading down to the bottom. So workers should be able to access these silos fairly safely. The big problem will be getting the welding equipment, the gas bottles, down into the bottom.
Now, they can be lowered down by rope.
Won't they be too heavy?
Not if they use the smaller sized bottles.
We'll need to specify the bottle size in the procedure then.
Yeah, they'll have to take care that the bottles don't fall onto someone as well, that no one's standing in the bottom of the silo while they lower them down.
True. That's another point to mention. Okay, so access isn't really a problem then. The main danger is the fact that it's a confined space, especially given that they're welding with an oxyacetylene torch burning, which will produce a fair amount of CO2.
So they'll need a CO2 detector.
I mean, to be safe, they'll need to test the air before they go down anyway. But we should probably specify that they need to keep the detector with them while they're working and keep it switched on.
Yeah. Another hazard is there'll be metal fumes given off as they're actually welding, which is a different problem to the CO2 issue.
Sure. So really, they'll need a ventilation system down there, some kind of air extractor.
Probably, yeah. And there's the problem of dust as well. They'll have to be very careful about that. If they're welding and there's grain dust in the air, there's going to be an explosion hazard.
Yeah. Would a ventilator clear the dust or make it worse? I suppose if there's a lot lying around, it'd keep blowing it up into the air, wouldn't it?
I'm not sure.
7.3.
Restricted areas are places where a serious danger is present, so it's essential that these should be kept locked at all times. Under no circumstances should anyone be able to access them unless they have a permit to work. In other words, a written form giving permission to work in the restricted area.
And the permits to work and the keys to restricted areas can only be issued by the electrical supervisor?
That's right. So that one individual is responsible for electrical safety for the whole plant. Only that person is authorized to issue permits to work.
Presumably, it's important that permits are issued every single time someone enters a restricted area. Each time they do a new job, they need a new permit.
Exactly. They shouldn't be issued for any longer than a full shift.
Okay.
And it's crucial that there's just a single key to each restricted area. The whole idea of having a lockout system is to ensure that only one person has access to switchgear at any given time. So whatever happens, someone cannot switch on a circuit at a switchboard while somebody else is working on it somewhere else in the plant.
If we imagine a technician needs to, let's say they're going to change a motor on one of the lines, they get a permit to work and obtain the key to the switchboard from the electrical supervisor. Then they take the key, unlock the door to the switchboard, switch off the circuit breaker for the motor to isolate it, then lock the door again.
That's right. Then, while they're working, it's vital that they keep the key on them continuously.
7.4.
The main hazard when maneuvering a helicopter close to power lines is the risk of a collision with the line. So before commencing work, it's essential for the crew to have detailed information about weather conditions, especially wind direction and speed. Operating in very windy weather is obviously out of the question. The pilots involved in live line work are highly trained and experienced, and their expertise is arguably the crucial factor in ensuring safety. Another hazard is snagging, as at certain times the platform will momentarily be attached to the power line and to the helicopter, leaving the aircraft tethered. It's essential, therefore, that the cable is equipped with a tension-release mechanism, so that if the helicopter pulls away suddenly for any reason, the cable can break free. To prevent electrocution and burns from arcing currents, the crew on the platform wear hot suits. These have stainless steel threads which channel the electricity around the technician's body, allowing the 400,000-volt supply to flow between the power line and the platform. The suits also have a fireproof lining to provide protection from heat. And eye protection is worn as a protection against flashes from electric arcs. Again, training is one of the key factors in ensuring safety. As a precaution against mechanical failure, the suspension cable, platform, and all associated equipment are systematically inspected before each operation to check for damage. And the helicopter is maintained in line with aviation regulations. One additional precaution is taken regarding the helicopter's engines. Only twin-engine craft are used for live line work, so that if an engine fails, the pilot can still land safely.
7.5.
The focus of the course will be on your personal obligations in terms of looking after your own safety and the safety of others. That means we'll be focusing on specific safety regulations. For instance, we'll be looking at personal protective equipment that's compulsory, or activities that are prohibited in certain areas, such as smoking. The majority of the obligations we'll deal with are legal requirements. In other words, they're stipulated by law as part of health and safety legislation. If you contravene these kinds of regulations, it's not the same as turning up for work late or merely breaching your contract of employment in some way. If someone fails to comply with health and safety regs, they're breaking the law. It's as simple as that. I'm sure you're all aware of that, but it is an important point to emphasise.
7.6. 1.
If there's a fire, you shouldn't use water extinguishers on this machine, because it contains electrical circuits and it can cause electrocution. You should only use a carbon dioxide extinguisher.
2.
When you lift this machine, it's essential that you should only use the 2 lifting eyes marked in red. No other parts of the frame are load-bearing, so you mustn't use them as anchor points.
3.
You should take care when you're cleaning below the guillotine blade, because there's a danger that the blade could come down. Before you clean it, you should always set the control lever in the blade-locked position. And you should wear protective gloves while you are cleaning it, because the sump below the blade can contain sharp metal offcuts.
8.1.
We know the client is a very green-orientated company, very big on all things environmental.
Absolutely.
So energy saving obviously needs to be an important consideration in the design. Clearly, it's a big subject and something we need to look into in depth. But one specific aspect of it where I think we can make a real difference is with the building management system, specifically with the way we use presence detectors. And I've had a couple of ideas that I'd appreciate your views on.
Sure.
I think we should put 2 totally different design options to the client. Option 1 is to have a building with maximum automation. So, with the maximum automation option...
8.2.
With the maximum automation option, we put presence detectors all over the place and link them to as many systems as possible. Not just the usual systems that activate the lights when people walk into rooms and turn them off when they leave. We could use presence detectors to control other systems as well, like the blinds on the windows. So, if it's the middle of summer and a presence detector senses that everyone's left a meeting room, a temperature sensor picks up a positive reading from sunlight coming through the glass. The electronics activate the blinds, which automatically come down and black out the room. That would limit heat absorption and reduce the load on the air conditioning, saving energy.
Okay.
Or in winter, if the blinds have been pulled down in the meeting room the evening before, the next morning the sensor detects sunlight and triggers the blinds to raise and let in as much sunlight as possible, contributing to the heating. And there could be temperature measurements to determine which rooms are the warmest, and those sensors set off a circulation system to distribute the warm air through the building, into the corridor or into rooms at the other side of the building or wherever.
So we'd use presence detectors and heat sensors to regulate as many systems as possible?
Yes. Well, that's what we'd have with the maximum automation option.
8.3.
The second option is this. It's a very environmentally conscious company, so I assume that green attitude is shared by all the staff. If that's the case, why is there a need to automate everything in the building when most things can be operated manually? Why doesn't the boss just circulate an email reminding people to switch the lights off when they go out and tell them to lower the blinds when they leave a room in summer so it helps the air conditioning? I mean, you'd save electricity because you wouldn't need to control all the systems automatically, and the money you saved by buying old-fashioned manual controls instead of high-tech electronics could be spent on planting trees or something. I mean, it sounds simple, but...
It's a very interesting idea. We have to bear in mind, of course, that the client's a manufacturer of high-tech electronic gizmos. I'm not sure how they'd feel about this in the long term.
8.4. 1.
The obvious danger here is that you could get a build-up inside the vessel if there's a blockage further along the pipe.
So the vessel needs a safety valve?
Yes, and maybe some sort of warning system as well. It could be something that's triggered by a differential measurement. So if there's a higher reading in the tank and a lower one further along, you'd know there was a blockage somewhere.
2.
We'll need a system for monitoring gas consumption.
What, a meter on the supply pipe?
Well, yes, that would measure cumulative consumption. But we also need to monitor the actual rate of consumption at different points in time during the reaction cycle. And if we have those two parameters, we can then determine the frequency of peaks in consumption, which is the third parameter we need.
So that's a software issue then. As long as the cumulative value is being recorded against the timescale, we can plot the rate of consumption against.
3.
The reaction that takes place is going to be exothermic, but the amount of heat will partly depend on how hot the gas is when it enters the vessel.
Yes, because that input heat can be adjusted.
Exactly. So we'll need a sensor next to the valve to measure the input value as gas comes in, and then another to give us an output value. Then we can work out the optimum input temperature for the gas.
8.5.
One of the biggest headaches in power generation is the fact that electricity consumption fluctuates considerably. So, in order to maintain a continuous supply, we have to make continual checks and adjust the power load we generate. To help us plan those adjustments, we forecast fluctuations in demand so that we can anticipate peaks and troughs. We base these forecasts on a number of different factors. One of them, one of the most important ones, is temperature. During periods of very cold or very hot weather, demand increases. The increase in demand is obviously due to millions of electric radiators coming on when it's cold and air conditioning units working hard when it's hot. Another factor, a key factor, which increases or decreases demand is whether or not it's light or dark in the morning and evening. Obviously, that dictates lighting consumption. So those are the two main seasonal factors. They generally go hand in hand, so on cold, dark, winter evenings, the rise in demand is significant compared with warm, light, summer evenings. We also take into account what day of the week it is, particularly whether it's a weekday or the weekend. Generally, demand rises during the week, when factories and offices are operational, and then decreases when a lot of them close at the end of the week. So demand falls at the weekend. Those are variations that take place within a given week. During any given day, there are factors such as meal times, when electric ovens are switched on. Obviously, that causes a jump in consumption. Even commercial breaks during popular TV shows can cause blips in demand. There can be a sudden rise when people rush to switch kettles on or heat up snacks in microwaves, and then a sudden fall shortly afterwards.
8.6.
Because electricity consumption fluctuates across a significant range, in order to cope with peak demand, our maximum capacity is equivalent to the top of that band of fluctuation. That means that during off-peak periods, we have significant spare generating capacity. Now, in an ideal world, it would be good to use that spare capacity to generate power and store it for use during peak times. Unfortunately, as you probably know, electrical charge is extremely difficult to store in large amounts. You can't just charge up huge batteries. So we use an innovative technique to store up power potential during off-peak periods.
8.7.
The concept of pumped storage is relatively simple. During off-peak periods, when main power stations have got spare capacity, some of the extra power they produce is used by pumped storage stations to pump water from a low-level reservoir up to a high-level reservoir, where the water's stored. It's then held there until there's a peak in demand at some point the next day. At that point, the water's released, and it flows down the pipes, driving turbines at the bottom, which generate electricity. Obviously, the station can only run for a fairly short period, but it's sufficient to cover the peak in demand. Then, as soon as there's a dip in demand, the water can be pumped back up and held ready for use again. So the effect is to smooth out fluctuations in the output of the main power stations. Some of the main stations' spare capacity is used when there would be a trough in the demand curve at night. The peak daytime generating capacity of those main stations can also be lower because the pumped storage stations are there to back them up when there are blips in the demand curve.
8.8.
Questionnaires like this drive me mad. I mean, look at this first question. What percentage of my time do I spend doing technical tasks that use my skills extensively? How are you supposed to put a number against that?
You only need to give a ballpark figure.
I know, but even so, it's difficult to say off the top of my head.
It's easier if you compare it with the second option.
Doing tasks that a less qualified colleague could do. Well, let's say roughly half and half.
Are you sure? Aren't you the least qualified person in this department?
Do you know, I knew you were going to say that. Number 2. Technical tasks that add value and tasks that don't add value, such as admin. Add value? What's that supposed to...
Well, do you not do some admin, or do you spend all of your time doing productive things?
Well, no. Nowhere near all of it.
Right, so is it 50-50?
Well, no. I spend more time problem-solving than I do on admin, thankfully. Let's say somewhere in the region of 2/3. So about 1/3 on admin. 3. Tasks that are purely technical versus tasks that relate to technical organisation. Well, most of what I do is organisation, isn't it? I spend pretty much all my time on that.
Or, in your case, disorganisation.
Nice one. What figure did you put down for added value, by the way? Was it a negative number?
8.9.
At this stage, I'm not asking you to give me a detailed breakdown of all the IT equipment we're going to need. It would just be useful to have a rough idea of what's most urgent.
Sure, well, one of the biggest problems is the screens at the CAD stations. A lot of those need replacing with bigger ones. Roughly speaking, I'd say well over half of them are too small. A good 2/3 of them, actually, so we're talking about 15 to 18 screens, something like that.
Okay. How urgent is that?
Well, I mean, they all work. They all function properly. The trouble is, the engineers spend the vast majority of their time working with these screens. And because the detail on them is so small, it's pretty hard work on the eyes, to the point that it affects productivity, so...
Okay, and what about the big printer in here? I've heard it's a bit of a dinosaur.
Well, it is, but it works perfectly well, and we print next to nothing with it anyway. Most of the drawings are printed at the factory.
Uh-huh.
9.1.
With the aerodynamics, there are 3 development tools available to us. The first is CFD software, Computational Fluid Dynamics. With that, the tests would obviously be virtual, based on a computer model. The second option is to go into a wind tunnel with a scale model or a full-size mock-up. In either case, we'd probably need to use a tunnel with a rolling road.
Would that be necessary?
Well, the thing is, the wheels generate a lot of turbulence when they're spinning, so to simulate that, you need a rolling road.
Yes, I know, but if we go for a bodywork design where the wheels are mostly enclosed, which is likely, would that be an issue?
Possibly not. It depends how fully enclosed they are.
Okay, I'm just raising the question.
Sure, it's something we can look at. The third option, then, is field testing, actually running the prototype outside on a runway or somewhere. So we can use these tools in isolation or as a combination. The question is, how can we gather as much data as possible with the limited budget we have?
Well, we need to bear in mind that the problem with Aero is that it's not just about data gathering. You also have to validate the data. CFD and wind tunnels are not 100% reliable. The acid test only comes when you try out a full-scale prototype in real conditions. We need to make sure that everything is tried and tested outside with a full-scale trial run.
Yeah, but let's not forget we're designing a car that does 100 kilometers an hour. It's not a supersonic aircraft. The Aero is not going to be that critical.
Plus, with changeable weather, it's not easy to do back-to-back testing out in the field.
No, of course not. I'm just saying we need to be careful. And we need to take...
9.2.
So, theoretically, the horizontal speed will keep decreasing until the container hits the ground. The higher the drop altitude, the lower the horizontal speed at touchdown.
Sure.
But obviously, the higher the altitude, the higher the vertical speed, up to a certain point.
Absolutely. So, assuming the drop altitude's very low, the vertical speed won't be all that high on impact.
True.
And in terms of protecting the cargo, surely a low vertical speed is the critical factor.
I'm not so sure it's the critical factor. I'd say the horizontal speed's more problematic. Because, presumably, if the ground speed's quite high, there's a danger the container will roll over and bounce along when it touches down. In fact, if you're dropping from low altitude, that's probably inevitable. So if the container rolled and bounced for 50 meters or whatever, then you'd have to have some kind of destructible external envelope to protect it from the multiple impacts, which would be very expensive. So, arguably, rolling is the worst problem, worse than a high vertical impact speed.
You think so?
So, you don't think rolling's a bad thing?
I'm not convinced the container would actually roll.
No?
Not necessarily. The military drop tanks out of flying aircraft at low level, tied to special platforms, and they just slide along the ground.
Oh.
And the systems that eject things out of the backs of planes are incredibly powerful. So, because obviously they fire the container in the opposite direction to the plane, that reduces the ground speed.
Uh-huh.
Plus, they use a parachute that deploys horizontally, which also helps to slow it down.
Of course.
So, based on what they do with tanks, I think we can safely assume that we can stop a container from rolling.
But a tank's got massive weight and a low center of gravity. With a smaller, lighter container, There's no way of knowing how it would behave, not without actually testing it. And even if you tested it 10 times, it would probably behave differently each time. It would be very unpredictable. Whereas if you drop from a higher altitude, okay, the vertical speed is higher, but with a lower ground speed, it would behave more predictably. And that would make it easier to design a cushioning system, because you'd be dealing with a single predictable impact.
Yes, but surely a heavy vertical landing is a huge problem. The force of it would be far greater.
9.3.
The first time we launched one of these things, we basically just got a plastic washing up liquid bottle, filled it about half full of water, then pumped it up with an ordinary foot pump.
So it was just ordinary household stuff?
Oh yeah, nothing too technical. And actually, there was a bit of a coincidence, because the opening in the bottle was just slightly bigger than the fitting at the end of the pump, so there was quite a good seal. So we pumped it up, one of us held the bottle while someone else worked the pump. And we released it, and it went up literally like a rocket. I mean, we expected it would shoot up reasonably fast, but we didn't anticipate just how powerful it would be. It just went whoosh and totally exceeded our expectations. So you can imagine us, a group of 12-year-olds, we were absolutely ecstatic. And having said that, there was one problem. Once all the water had come out, which happened virtually in a split second, the bottle, because it was very light, started tumbling over in the air.
So it wouldn't fly straight?
That's right. But we quickly came up with a solution to that problem.
9.4.
What we did was to get a plastic cup, a strong one, not a disposable cup, and pushed it onto the end of the bottle at the top to form a nose. It didn't go exactly according to plan at first. It stabilized it a bit, but it still wasn't flying straight. So we tried putting water in the beaker to act as ballast, and that worked a treat. With the extra inertia and the fact that it was front heavy, it went like an arrow. So yes, we sorted that problem out. Then the next goal was to increase the power to try and reach a higher altitude.
9.5.
One of the things we did was to experiment with the amount of water inside the bottle. I think initially we expected that the more water we put in, the more powerful it would be. But as it turned out, it was the opposite. What actually happened was, if you overfilled it, there wasn't enough pressure to expel all the water. We reduced the amount of water to about a quarter or a third full, something like that. And we also put some tape around the end of the pump to get a better seal with the bottle. That was really effective. I think we underestimated the pressure we were generating. And certainly we were overestimating the strength of the bottle, because it got to the point where we were firing these rockets up to, I don't know, maybe something like 20 meters high, something like that. So you can imagine the sort of pressure involved. And plastic bottles are hardly up to the job of high-pressure rocketry, obviously. So inevitably, the bottle eventually blew up while I was holding it. I was rolling around on the ground with sore hands, while everyone else was rolling about laughing. So I learned the hard way.
9.6.
So how credible is this hoax theory then? I watched a documentary about it a while ago.
Well, some of the questions are quite interesting, but from what I've read, they can all be explained scientifically. You know, like the fact that the stars aren't visible in the sky on the photos. Apparently, it's just due to sunlight on the surface of the moon. It was too bright to see them, that's all.
Isn't the flag supposedly waving in the wind in one of the shots?
Yeah, that's right, yeah. They say it's because of the pole shaking after it had been stuck in. There's obviously no air, so as a result it kept moving for ages due to the fact that there was no friction to slow it down.
Oh, I see.
Another thing that's been explained is the footprints on the surface. People had said the ground looked wet, so it couldn't have been on the moon. But apparently that's the way that type of dust behaves in a vacuum. It sticks together like mud.
Wasn't there some other theory to do with dust when the module landed? That there should have been more dust or something?
Well, during the landing there was supposedly a lot of dust flying up, caused by the blast from the engines. But when the module's actually seen on the surface, there's no crater visible below it. So the theory is that if it had really landed there, it would have left a crater. But the argument against that is that it had already slowed down substantially by the time it reached the surface, and it was only descending gently because of the low gravity.
Oh. So there was only a bit of surface dust blown up?
That's right.
10.1.
Obviously, a tubular steel tower only gives you sufficient structural strength if you give it adequate protection from corrosion, the big problem with offshore installations. So technically, you could say steel is inappropriate in that environment.
They make ships out of it.
I know, Loretta, but only because there's no cost-effective alternative. But we're not talking about ships. We're talking about fixed structures. The point is, I think we should look more seriously at alternatives to all steel supports. And the obvious alternative is reinforced concrete.
We've already looked into it, though, and it wasn't cost-effective.
Not in the short term, but we didn't really look into it properly over the long term.
But you made the point yourself, Mike, that steel is completely ineffective if it's corroded. And one of the main constituents of reinforced concrete is steel.
It's protected, though, isn't it? It's embedded inside concrete. That's a much more effective protection than paint.
Not necessarily. If we're talking about the long term, as you say, what happens to concrete when it's exposed to the sea for a few years? It erodes, which means the steel eventually gets exposed. You look at concrete coastal defenses. How often do you see the concrete all crumbling away and all the steel exposed?
That's due to inconsistent quality, though. You only get that problem if there's insufficient cover. As long as there's appropriate cover at design level and the construction quality is consistent, then there shouldn't be a problem.
Isn't inadequate cover more of a problem in a slender structure, though? You'd probably have less cover compared with the big lumps of concrete they use for coastal defences.
Not if...
Just a second.
Yes, Hanif?
Let's just think about what we're trying to resolve here. The key issue is, what's the most suitable long-term solution? And in both cases, we're saying steel is necessary, either in an all-steel tubular structure or in the form of reinforcement inside concrete. But obviously exposed steel is unsuitable because of the problem of corrosion. So the question is, what's the most reliable way of protecting steel over the long term? And we have to bear in mind that just because something requires regular maintenance, such as painting, that doesn't necessarily mean it's unreliable. As long as the maintenance is consistent, the key question is, what's the most economical approach? So, painting a steel structure every couple of years is uneconomical only if the cost of painting is more expensive than the additional cost of using concrete at the time of construction.
So, to determine the most efficient solution, we need to assess the lifespan of a reinforced concrete structure. If we know that, we can determine how many times the equivalent steel structure would need to be repainted over that same period, and what the cost of that would be.
Yeah.
But this is really the point I'm making, Hanif. We can't categorically say that reinforced concrete is inefficient unless we look into it in detail.
Of course not. Look, let me make a suggestion. I was thinking...
10.2.
With very tall structures, one of the main loads you need to take into consideration clearly is the mass of the structure, its weight. Due to gravity, that mass exerts a downward load which has to be transmitted to the ground. So that downward force means the structure is in compression, especially near the bottom. Obviously, the closer you are to the bottom, the more compressive force the structure is subjected to. But with tall structures, downward load compressing the structural elements is only part of the problem. Another major force acting on the structure is wind load, which is a horizontal load exerted by air pressure against one side of the structure. Because the structure is fixed at ground level and free at the top, that generates bending forces. And when elements bend, you have opposing forces, compression at one side, tension at the other. And at ground level, the wind effectively tries to slide the structure along the ground, and the foundations below the ground resist that. The result of that is shear force between the substructure and the superstructure. The wind generates tensile loads on the foundations of tall structures as well, as the bending action tries to pull them out of the ground on one side. A bit like a tree being uprooted by the wind. So the foundations need to rely on friction with the ground to resist the pull-out force, just as tree roots do. The action of the wind can also generate torsion. You get a twisting force sometimes when the air pressure is comparatively higher against one corner of a building. Although that's less of a problem with chimneys because of their circular profile. With very large masses of concrete, you also have to think about the forces generated by thermal movement. When concrete absorbs heat from the sun, you get expansion. As soon as the sun goes in, there's contraction. That movement can be significant over a large area, especially as the sun generally heats one side of a structure much more than the other. So there are all kinds of different forces acting on a tall structure.
10.3.
The record speed exceeded the standard operating speed by a huge margin. It was 80% faster at its peak. So you would imagine that the TGV used for the record run was heavily modified. In fact, that wasn't really the case. The train was modified to a certain extent, but with a few exceptions, it was essentially just an ordinary TGV. As you can see from this slide, one of the biggest differences was that the modified train was significantly shorter in order to make it lighter. There was a 50% reduction in length down to 100 meters, compared with the 200-meter standard length. The coaches being pulled were perfectly standard. The only differences were that some of the seats had been removed to make way for all of the monitoring equipment that was carried on board. And some changes were made to the bodywork to make it slightly more aerodynamic, which meant the drag coefficient was reduced by 15%. The wheels on the modified train were marginally bigger than the standard size. The diameter was increased by 19% in order to reduce the speed of revolution, to limit friction and centrifugal force. And the power of the electric motors was substantially higher than the standard units, boosted by 68%. But none of the changes was fundamental. So my point is, standard high-speed trains can be made to go faster by a considerable amount.
10.4.
In the late 1940s and early 50s, the United States Air Force carried out a series of experiments to explore how much physical stress the human body could withstand. A key aim was to test how much G-force pilots were able to cope with and see what would happen if they exceeded their limits. Led by Air Force Dr. John Paul Stapp, a number of spectacular tests were carried out at Edwards Air Force Base in California, a location suitable for the experiments thanks to its 600-meter rail track, specially designed for high-speed rocket tests. A rocket sled capable of reaching speeds approaching the sound barrier was mounted on the track. On top of the sled, named Sonic Wind, researchers fixed a seat intended for an abnormally brave volunteer. refusing to give the dangerous job to a member of his team. The man in the hot seat was John Stapp himself. Over several runs, Stapp was subjected to progressively greater extremes of force. Each time, he resisted. Eventually, the time came to take the ultimate risk, to surpass what many doctors believed to be a deadly level of G-force. And so, on December 10th, 1954, Stapp was strapped onto Sonic Wind for the mother of all rides.
10.5.
That day, Stapp was subjected to extremes of force beyond the imagination. When the sled's rockets fired, he shot from 0 to over 1,000 kilometers per hour in just 3 seconds, subjecting him to 20 Gs. When the sled hit the pool of water in the braking zone, it was like hitting a brick wall. Stapp slowed from the speed of a bullet to a complete stop in little more than a single second. Incredibly, John Stapp survived the ride, although so much blood had rushed into his eyes that he was unable to see for some time afterwards. Before the test, doctors had believed that human beings were incapable of surviving forces greater than 17 Gs. When the sled hit the water, Stapp had pulled a crushing 46 Gs.
10.6.
I think what he's suggesting in terms of acceleration and deceleration forces is reasonable.
Yeah. 2G sounds about right. Anything less than that, and the track length's going to exceed the size of the site. And if you start getting close to 3G or beyond that, then that's probably going to be a bit too much for the average passenger.
I'd say so. His calculations for the total distance for acceleration and deceleration seem about right. The problem I have is with the length of the track. I think his 10-kilometre figure is okay for an ideal world scenario, but it doesn't leave much margin for error.
No, because at full speed you're going to be covering, what, a kilometre every 3 seconds? So if there's some kind of problem, you're going to be eating up the kilometres at a pretty frightening rate.
You can say that again. I think he'll need every kilometre of track length he can get on that site, plus some sort of emergency stopping facility at the end of the line, just in case.
Definitely, yeah.
Then I don't know what you think about using wheels instead of skids.
Well, technically, it's feasible to build wheels capable of spinning at that sort of speed, because it's been done on land speed record cars. The only problem is, if you get a wheel failure at the kind of speeds we're talking about, the consequences are going to be unthinkable.
Yeah. I haven't calculated exactly what centrifugal forces they'd have to cope with, but for wheels of about 500 mil diameter at full speed, I worked out they'd be spinning at over 13,000 RPM.
Yeah, that's a lot. Plus, of course, skids should give better frictional resistance under braking.
Possibly.
Maybe not?
Well, the friction from wheel bearings spinning at that sort of speed might be higher, and the skids wouldn't be in permanent contact with the rails, don't forget. But anyway, I think skids are the only safe option.
I'd go for skids, definitely.
And then for the brakes. I think the first point is that for the initial deceleration, even without applying any brakes, the aerodynamic resistance is going to be huge. In fact, that alone might even exceed 2G for a short time.
Possibly. It'd depend how much drag there was, which obviously depends on the bodywork design, doesn't it?
Yeah.
I don't like the idea of a friction system against the rails. It would have to withstand a tremendous amount of heat.
Yeah, I think that's a non-starter at these kinds of speeds. Aerodynamic braking has got to be the best option. Possibly you could deploy flaps initially at top speed, then maybe release a parachute as a second stage. Yeah, maybe deploy the parachute at, I don't know, what sort of speeds do dragsters reach? They use parachutes, don't they? What do? 400 Ks?
A bit more, I think. 450, something like that. There's also the option of reverse engine thrust, like they use on aircraft.
In that case, though, you'd still need another system, in case you get an engine failure. But it's a possibility. I think the bottom line is that it needs a combination of systems to make it absolutely fail-safe.